Okay, this is lecture number 24 where we cover view factors. My pen's been acting up, and for some reason it's better if I write in this ridiculously thick line, so forgive me. Hopefully you can still read it okay. So lecture 24, which will cover, although apparently it's not any better, view factors. Okay, so in chapter 12, we covered a lot of stuff that felt like physics, right? We talked about changes with wavelength. I'll write a lambda. That means we talked a lot about how emissive power changes with wavelength, how irradiation changes with wavelength, emissivity and absorptivity. We also focused on one surface. So although we did a few homework problems that talk about exchange between a few surfaces, in general we focused just on what's happening at one surface. So it didn't really feel that useful, right? But now we are getting into chapter 13. Chapter 13 alternatively focuses on multiple surfaces. So now instead of just one surface where we have some defined irradiation approaching, we are going to have a series of surfaces, often enclosed, kind of like this triangle, and we're going to call that an enclosure, or several surfaces that are touching and exchanging heat with each other. And we're usually curious to find the temperature of some surface or what the rate of heat transfer is between surfaces. That's what chapter 13 is going to be all about. Okay, and in order to do that, we're going to have to make some assumptions. These are universal assumptions for all of chapter 13. And the first is an assumption that we've made before and that we will make again: diffuse, meaning we have emission or irradiation that is constant in all directions. So it's emitting the same in all directions. We're also going to say that our surfaces are gray. So in class, I went over a pretty long example of what it means to be gray again, because I really think that's useful. However, I'm not going to cover that in this lecture. This lecture, I'll skip straight to view factors. I'll make a separate video talking about gray surfaces that you can watch to review for the test. Okay, and then also we're going to say all of our surfaces are opaque, which means any irradiation is either absorbed or reflected. None of it is transmitted through, like glass. Visible light is transmitted through glass, so glass is not opaque. Okay. So we've reviewed those things. So instead of, again, going over the gray example, I'm going to post a separate video. And here we're going to skip straight to chapter 13. Okay, I forgot to make my thing really big, so we're just going to keep refreshing the screen. Okay, so we get straight to chapter 13, which today all we're covering is section 13.1, view factors. Okay, so the first and most important thing, what is a view factor? Well, isn't it great that the book decided to use capital F to designate a view factor, just like the fractional function, so don't get those confused, okay? So let's define what it is. Well, let's say we have a surface, which I've drawn down here, surface I, and we have a surface up here, surface J. Okay, so we've got heat that's leaving surface I in all directions. And some of that heat is going to hit surface J. Okay, so the view factor is defined as, of course, my pen starts to freak out now, as the heat transfer from surface I to J. So that's specifically just this line I've drawn right here, the heat transfer that goes from I to J. And that's divided by the heat transfer from I. So that would be all of these arrows. So really, the view factor, in this case, Fij. So the view factor from I to J, or the amount of heat leaving I that's going to hit J divided by the total amount of heat leaving I. So it's just a fraction, the fraction of heat that will hit a certain surface from a certain surface. Okay? So this is actually very useful because let's write out kind of a more mathematical definition. So Fij, let's say Qij is the heat transfer from I to J. And then let's say Qi is the total heat transfer from I. Well, the total heat transfer from I can be rewritten as just the radiosity of surface I times the area. Remember, the radiosity of a surface, if this is I, is equal to what's emitted plus what's reflected. So these two things make the radiosity. Okay? So if we rewrite it this way, then we can rearrange these two things to get, that's Qij equals the view factor between Ij times the radiosity of I times the area of I. So look at that. That's a super nice small equation that tells you the heat transfer between two surfaces. And all you have to know is the radiosity, the area, and the view factor. We don't have to mess around with that intensity stuff or solid angles or any of that garbage. We just need to know the view factor. And this also works for black surfaces. So we just wrote, just to refresh, Qij is the view factor from I to J times the radiosity of I. So that's all the energy leaving I, reflected plus emitted. Okay, so that's for any diffuse surface. Okay, but we can also write one for a black surface. So again, the heat transfer between surface I and J is just the view factor between I and J times now by the emissive power of I times the area of I. And that works for a black surface because think about a black surface. Everything leaving a black surface, which we would think of as radiosity, is just emission because anything incoming is absorbed. So these are pretty cool equations because they're super simple to use, but they tell you rates of heat transfer. So we really want to use these equations, but there's kind of a big question mark, right? This guy right here. So great, we can use view factors, but we've defined them using heat transfer, when that's usually what we want to find. So can we find view factors a different way? And indeed, we can. So I'm not going to derive for you this equation. It is derived in your book in section 13.1, but I'm just going to write it. So by definition, the view factor, the view factor between two surfaces, again, we're going with I and J, which I'm going to draw here and here. So this is I right here. This is J right here. Okay, so the view factor between them is defined simply as 1 over the area of I times the integral, two integrals. One integral over the entire area AI and one over the entire area AJ. So what we're going to do is say that these are differential areas. Okay, so that's a differential area I, and this is a differential area J. And we're doing that, and we're going to say that there's some bigger area, right? So these are differential areas of some bigger area, AI and AJ. Okay, so What's inside this integral? Well, we've got the cosine of theta of I, where if this is our normal and this is the line between the centers of our differential areas, this would be theta I. And if this is the normal, that right there would be theta j. Okay, and then this line between the centers has distance r. Okay, so the view factor is cosine theta I times cosine theta j, all divided by pi r squared times our differential area j. See, this differential operator is related to this integral. So we're integrating this expression over the entire area j. So we're moving this little differential area all around our area j, which changes r and theta j, and integrating this. And then we're also doing this integral all over area I. So we're moving this differential area in all over area I, integrating this with respect to this location, which changes r and theta I. And that right there is the definition of a view factor. The most important thing here is the word geometry. Write this in your notes. You notice that all these things in this equation only depend on geometry. There's no temperature, there's no emissive power, there's nothing besides geometry. So that's really nice, because if you know the geometry you're looking at, then by definition, you know the view factors. Just real quick, let's rewrite that equation to help you get a little bit more intuitive understanding of kind of what's going on there. So again, we had cosine theta I and cosine of theta j, all divided by pi r squared, that's r squared, times daj times d, come on, ai. Okay, now the reason I wanted to bring this up was because there's actually parts in here you recognize. Like, for example, look at this right here. Cosine theta j divided by r squared times daj. So that actually looks a little familiar, right? Cosine, my pen's kind of screwing up. Oh, goodness. Well, it's written here. Cosine theta j times differential area divided by r squared. That right there is a solid angle. The solid angle of j with respect to surface I. And then further, you see right here, cosine theta I times dai. Those things are projected area. The projected area of surface I. And then there's pi right here, just converts everything into steradians. So you see, this has elements we recognize. And in fact, to derive it, we started with the fundamental definition of intensity, and then we solved for Q and divided it by what Qi would be, and we got this, the view factor. Okay, so now remember, it only depends on, oh my goodness, on geometry. But despite the fact it only depends on geometry, it is nonetheless a very nasty integral. Look at this thing. Nobody wants to do this garbage. So, luckily, someone has done it for us, and they have tabulated their results into a table. And that would be table 13.1. In table 13.1, and I was going to bring this up, but I guess I've forgotten. In table 13.1, you get these entries. So one will be like, the first one looks like this. Look it up in your book right now if you have a chance. Pause and look up table 13.1 in your book, and then resume when you're there. Okay, so table 13.1. This first one, for example, tells you you've got two parallel plates with their centers aligned, and it tells you how wide those plates are, W1 and W2, and it tells you how far apart those plates are, L. And then it gives you, in the next column, the view factor between surface 1 and 2, although it uses I and J, I believe. And, it's some kind of long, crazy equation, something like this. Big W1 plus big W2 squared plus 4 all to the 1/2 minus some more stuff divided by 2 big W1. So you've got this big equation, and it defines what big W1 is for you, which is little w1 over L, and what big W2 is for you, which is little w2 over L. So you see, this gives you an equation, just like a correlation, that you can use to find the view factor between surface 1 and surface 2. So that's pretty cool, right? And this table is a little small, but it still has some pretty useful geometries, like two parallel plates. It also has two plates that are the same distance, the same width, separated by some angle. It's got two cylinders that are a distance apart. You name it, it's got it. But that's just the table. It doesn't always have everything you're looking for. So alternatively, if it doesn't have a view factor that you need, then go to this website, thermalradiation.net. It is a very old website, like straight out of the 90s, /index-cat. Then again, most of you are from the 90s, am I right? Indexcat.html. Okay, so go here, and you can look up literally 100 or so different view factors for any geometry you can ever think of. Okay, there are a few other methods. Specifically, there are numerical methods, which anytime you use like a heat transfer solver in ANSYS or something like that, it's using a numerical method to find the view factors between all of the different surfaces, and then it's solving all of the heat transfer between those surfaces using the view factors. But we're not going to cover that. Okay. So those are kind of the different methods you can use. There's the tables, there's this website, there's numerical methods, but then there is one more thing you can do. And this is what we're going to spend the rest of this lecture doing, which are view factor relationships. Okay, so view factor relationships are kind of like view factor algebra. There are 6 rules that you can use in order to simplify a geometry or to break down a geometry into more basic forms, or to really, you can use these even to define certain geometries without having to use any tables or anything, and we're going to do that at the end of the class. Okay, so I'm going to go through these 6 rules and then do 2 basic examples for you to see how you would use these rules. My hope is in this class, aside from this homework on like the test and in this lecture, you won't need to use tables or lookups for anything. You can just use these view factor relationships to find some view factors. Okay, so let's go over it. We have rule number 1, which I will call the unity rule. So this is rule number 1. Okay, let's say you have a surface like this and another surface like this. This is surface 1 and this is surface 2. Okay, so the view factor from 1 to 2, that's 1 to 2, is equal to 1, or unity. Okay, and that's by a fairly basic line of reasoning, which is, remember, the view factor is the fraction of heat leaving surface 1 that hits surface 2 divided by the amount of heat leaving surface 1. Well, check this out. Anything leaving surface 1 has to hit surface 2 because surface 2 completely covers surface 1. Okay, so if a surface possesses the full hemisphere of another surface, then that surface has a view factor of 1. But don't be confused. F2, 1, so the view factor of heat leaving 2 that will hit 1 is not 1. Okay? And that's because heat leaving 2 doesn't necessarily have to hit surface 1. It can hit itself, which means view factor 2 does have a view factor of not 1, of not 0, I'm sorry, with itself. Oh my goodness. So the view factor from 2 to 2 is not 0. Okay, so that is rule number 1. Let's go over rule number 2, which we will call the reciprocity rule. Oh my goodness. Reciprocity, you get it. Okay. So the reciprocity rule is fairly simple. It looks like this. If you have a view factor Fij, that's Fij, and you multiply it by the area of I, so the area of the first letter, or where heat is leaving from, then that is equal to Fji times A. Give it a second. Times Aj. So you see, all we've done is switch the letters on our view factor. So this is now j to I and multiplied by j. And so what this lets you do is, if you know a view factor from 1 to 2, for example, you can find the view factor from 2 to 1 just by knowing the areas. So as an example, let's go back to our first example. We've got this, oh my goodness, this hemisphere covering surface 1. So surface 1 and surface 2. So we already know by the unity rule that view factor from 1 to 2 has to be 1, okay? But we already said the view factor from 2 to 1 is not 1. Then we can now prove that to ourselves, because we can say, well, the view factor from 1 to 2 times area 1 has to be equal to, using the reciprocity rule, the view factor from 2 to 1 times area 2. So coming down here, we can then solve for the view factor from 2 to 1, which is just equal to, remember, this is 1, so we're just going to leave that as 1 and ignore it. That's just the area of 1 divided by the area of 2. All right? So we just take the ratio of these areas, and you actually have the view factor between surface 2 and surface 1. Pretty cool, huh? So that's rule number 2, reciprocity. Okay, let's do rule number 3, which is the symmetry rule. Okay, so we've got a triangle. As soon as I can draw a triangle. There is our triangle. There's surface 1, 2, and 3. Now this is a triangle, which means if we draw a line down the middle, then this triangle is the same on the left and the right. So if I were to flip it horizontally, like rotate it like this, 180 degrees, so surface 3 was on the left and surface 2 is on the right, it would look exactly the same. And remember, view factors depend on geometry. So because of that, we can invoke a symmetry rule and say that the view factor from 1 to 2 must be the same as the view factor from 1 to 3. Right, so the amount of heat leaving 1 that's going to hit 2 is the same as the amount of heat leaving 1 that's going to hit 3, because since energy is emitted uniformly in all directions, it's going to hit 2 and 3 equally. So that is the symmetry rule. Okay, so that's rule number 3. Let's get to rule number 4. Which is, wow, let's see if this, maybe if I go really slow. The summation rule. Summation. Okay, let's go back to our triangle example. All right, so here is surface 1, here's surface 2, here's surface 3. So we just talked about view factors being the same, right? But also, all of the energy, all of the heat leaving 1 is going to hit surface 2 and surface 3. And as we see, it's only going to hit surfaces 2 and 3 because 2 and 3 entirely cover the surface. So remember that the view factor from 1 to 2, for example, is just the amount of heat that hits 2 from 1 divided by the amount of heat leaving 1. And the view factor from 1 to 3 is just the amount of heat leaving 1 that will hit 3. Well, the amount of heat leaving 1 only hits 2 and 3, which means if we add those view factors together, we have to get 1. So the summation rule tells us that heat leaving from, in this enclosure, from 1 must, to all other surfaces, must add up to 1. So now if we have like a 5-sided enclosure, then we could write the summation rule from this surface, I'm drawing arrows from, to that surface. So the view factor from surface 1 to surfaces 2, 3, 4, and 5 must add up to 1. So that is the summation rule. Okay, next we have what I'm calling the curvature rule. But that's not entirely descriptive of what's really happening, but just for kicks and giggles. So here we've got surface 1. And here we've got another one of these semicircles, surface 2. Okay, well, I'm going to take a piece of hypothetical saran wrap and stretch it over the opening of surface 2. And we will call that surface 3. Surface 3 doesn't really exist. It's not physical in any way. But we could draw it and call it a pseudo-surface. Okay? Oh, excuse me. Now, the view factor from surface 1 to 2, right? So the fraction of energy leaving 1 that's going to hit surface 2 is going to be the same as the view factor from 1 to 3. This we'll call the curvature rule. And that's because, see, we've got heat, it's leaving 1, it's going to hit surface 2. And we've got heat leaving 1, it's got to hit surface 2. Just like this. Now, any heat that's going to hit surface 2 has to pass through surface 3 in order to do so. Which means any heat that's going to hit 2 must hit 3. So the amount of heat hitting 2 is the same as the amount of heat hitting 3. So the view factors are the same. That's the curvature rule. And it only works going into the concave surface. So the view factor from 3 to 1 isn't necessarily the same as the view factor from 2 to 1 because 2 sees itself, but 3 does not see itself. Okay, the last rule. Number 6. Partition. Okay, let's say we've got, we'll try over here. Kind of this plate, and it's connected to another plate at a 90-degree angle, and we will call this whole thing right here surface 1. And we're going to split this into 2. We're going to call the whole entire upper surface surface 2. And we're going to call each of these individual surfaces 3 and 4. Okay, so you could probably see where this is going, but the view factor from 1 to 2, so the amount of heat leaving 1 that's going to hit 2 divided by the total amount of heat leaving 1, has to be the same as the view factor from 1 to 3, being only this part, plus the view factor from 1 to 4, being only this part. Because when you add those together, you get surface 2. So the amount of heat leaving 1 that hits 3 and 4 must be the same as the amount hitting 2. Again, seems kind of like a duh, but it's also nonetheless true, so I'm telling you. So that's the partition rule, and that is the last of the rules that I'm going over today. Honestly, you can't find all these rules in the book. Only 2, being summation and partition, are really official. And and let's see, the real rules are reciprocity, summation, and partition. The rest, the book just assumes you'll figure out, but I'm telling you because I am nice. Okay, so now that we understand the 6 rules, the 6 view factor relationships, I am going to give you several challenges. So here is challenge number 1. Okay, challenge number 1 looks like this. We're going to go for a triangle again. Here's surface 1, 2, and 3. And the way this surface works out, this triangle, I think it's isosceles is the right name. The length of 1 is half the length of surface 2 and of surface 3, where L is the length of the surface. So surface 2 and 3 are the same, and they're both double the length of surface 1. Okay? Now I want you to find for me the view factor from 1 to 2 and the view factor from 1 to 3, using only view factor relationships. Oh, and the view factor from 2 to 3. Again, using only view factor relationships. So you shouldn't have to look anything up in the book. You should just be able to do it using the 6 rules. So I'm going to ask you to pause and try and do that, and then come back to the video once you're done. Okay, assuming you did that, let's go over how to do this. Okay, so first, I'm just going to kind of state things as I use them. So view factor from 1 to 2, we're right away going to say is equal to the view factor from 1 to 3. And that is because of symmetry. So the symmetry rule tells us that because we can draw this vertical line down the middle, and it's the same on the other side, F1 to 2 equals F1 to 3. Okay? But then we also know that F from 1 to 2 plus F from 1 to 3 has to equal 1. That's the summation rule. In fact, when we talked about the summation rule, we used a triangle as an example. Because this is an enclosure, all the heat leaving 1 must hit either 2 or 3. So you add those v factors, you get 1. Okay, well that's nice because 1 to 2 equals 1 to 3. So we can put f1 to 2 as f1 to 3. And you're left with 2 f12 equals 1. So that means f12 is 1/2. There it is, which consequently is equal to f13, also 1/2. Okay, let's do f2 to 3. That one's a little trickier, right? So now looking at 2, let's do f2 to 3 plus f2 to 1 equals 1. That's the summation rule. Okay, so we say, all right, well, f23 is what we're looking for. We don't know f21, and we're not sure how to find it, but we do know f12. So is there a rule that tells us the relationship between f21 and f12? Well, yes, there is. That would be reciprocity. So f12 times a1 equals f21 times a2. That's the reciprocity rule, which means f21 equals f12 times a1 over a2. Now I'm going to start using the L notation, which I should have done from the beginning, because our areas, we're saying this is 2D, not 3D. Okay, well, we know f12, it's 1/2. We know that L1 over L2, so if we know that L1 is half the size of L2. So if this were 1, this would be 2. So that means the ratio of L1 to L2 is 1/2 as well, and we get 1/4. So 1/4 of the heat leaving surface 2 is going to hit surface 1. Kind of interesting, huh? Oh, wait, no. That's 2 to 1. I asked you for 2 to 3. So we plug that back in there, and we get f23 plus 1/4 equals 1. So f23 is 3/4. So 3/4 of the heat leaving 2 will hit 3, which is interesting, right? Okay. The next challenge I'm asking you to do is a circle. Here's our circle. Actually, I'm sorry. It's not necessarily a circle. It's 2 half circles which have been put together. Think like a coconut. You cut it in half and then put them back together. So we've got surface 1 and surface 2. This circle has a diameter of d. I want you to find f from 1 to 2. And I originally asked for f from 2 to 1, but that's kind of easy. Okay, so how are we going to do it? Well, first we draw. So let's redraw our circle. 1 and 2. And we're going to draw another line, 3. We're going to use the curvature rule, right? So we know that f from 1 to 3 is equal to f from 1 to 2. Right? So the curvature rule told us that everything leaving 1 that's going to hit 2 has to hit 3. So f from 1 to 3 equals f from 1 to 2. All right. Well, then we say, let's use the reciprocity rule. So f13 times area 1 is going to be equal to f31 times area 3. So that's reciprocity. Okay, so now we know that f13 equals f31 times a3 over a1. And you say, well, How does that help us? Well, let's look at F31. What would F31 be? Well, check that out. 1 entirely covers surface 3. So we know that's 1 because of the unity rule. That's supposed to say unity. Unity. You get it. Unity rule. Okay, so we can plug that directly in there. And now we just need to know what the relationship between A3 and A1 is. Well, if you look up here, 3 is just the diameter of the circle. So we can write A3 as D, the diameter. So then what is A1? Well, A1, sorry, I'm frozen. Hopefully it works out. Oh, there we go. A1 right here is half of the circumference. So what is the circumference of a circle? Well, it's pi times d. We already said it's half of it. So the d's cancel and we're left with 2 over pi. So f from 1 to 3, which is equal to f from 1 to 2, is equal to 2 over pi. Okay. I have one more challenge for you that I'm not going to do right now on this video. Instead, I'm going to do this like Good Will Hunting, where I leave this challenge for you to solve. And on Tuesday, I said the first person to solve this would be declared the Emperor of Heat Transfer. And I leave that challenge with you, although I'll have you know the challenge has already been accomplished by a student in the class. But think of the satisfaction you will get in knowing that you figured this out. So here you have a square. I want you to find f from 1 to 2 and f from 1 to 3 using only the 6 rules that I explained earlier. You can do this using the table in the book, but you also can do it using only the 6 rules. And yes, like I said, the first person to send me a proof of this challenge using only the 6 rules will be declared the Emperor of Heat Transfer. Okay, so that's about view factors. I'm looking forward to Tuesday when we'll use view factors to solve the radiative heat transfer inside an enclosure in order to find the Q between the surfaces and the T of the surfaces using, you guessed it, a circuit analogy. So get excited. Okay, see you on Tuesday.